In this video, we will explore the Transmission Control Protocol or TCP in depth. We will focus on understanding the core of reliable network communication. The topics covered include the three-way handshake, flow control and windowing, reliability mechanisms, and connection management. This slide presents an overview of the Transmission Control Protocol, or TCP. TCP is a Layer 4 protocol in the TCP or IP model. It is a connection-oriented protocol, providing a reliable data transfer mechanism. TCP ensures that data arrives complete and in the correct order. It achieves this reliability through the use of sequence numbers and acknowledgements. TCP also implements flow control and congestion avoidance techniques to ensure efficient and reliable communication. Let's delve into the structure of a TCP header. The TCP header includes several key fields. The source port, which is 16 bits long, and destination port, which is also 16 bits long, identify the sending and receiving applications. The sequence number, which is 32 bits long, identifies the position of the data in the stream. The acknowledgement number, another 32-bit field, indicates the next expected sequence number from the sender. The header also contains several flags, along with the data offset field, a reserved field, and a window size field. The flags are control bits that manage the TCP connection. The header also contains a checksum field, which is 16 bits long, and an urgent pointer field, which is also 16 bits long. The sequence number identifies the position of the data in the stream, while the acknowledgement number indicates the next expected sequence number from the sender. The flags field contains control bits such as the SYN, ACK, FIN, RST, PSH, and URG flags. The window size field controls the flow of data, specifying the number of bytes the receiver can accept. The Transmission Control Protocol uses a mechanism called the three-way handshake to establish a reliable connection between two devices. The first step is the client sends a SYN packet to the server, indicating that it wants to establish a connection. This SYN packet includes an initial sequence number, represented as SYN equals 1, SEQ equals X. The second step is the server responds with a SYN ACK packet. This acknowledges the client's SYN and includes the server's own SYN. This packet is represented as SYN equals 1, ACK equals 1, SEQ equals Y, and ACK equals X plus 1. The third and final step is the client sends an ACK packet back to the server, acknowledging the server's SYN. This completes the three-way handshake, and the connection is established. The packet is represented as ACK equals 1, SEQ equals X plus 1, and ACK equals Y plus 1. The Transmission Control Protocol uses a four-way handshake to terminate a connection. This process ensures that both sides of the connection agree to end the session, preventing data loss. First, the client initiates the termination process by sending a FIN packet to the server, represented as FIN equals 1, SEQ equals X. Secondly, the server acknowledges the client's FIN packet with an ACK packet, represented as ACK equals 1, ACK equals X plus 1. Thirdly, the server sends its own FIN packet to the client, indicating it is ready to close the connection, represented as FIN equals 1, SEQ equals Y. Finally, the client acknowledges the server's FIN packet with an ACK packet, completing the termination process, represented as ACK equals 1, ACK equals Y plus 1. This process is also known as the four-way handshake. Transmission Control Protocol uses a sliding window mechanism to control the flow of data between the sender and receiver. The window size determines how many bytes can be sent before an acknowledgement is required. The receiver advertises its available buffer space in the window size field of the TCP header. The sender then adjusts its transmission rate based on the receiver's advertised window size. This prevents the receiver from being overwhelmed with too much data. The window size can change dynamically during the connection, allowing the transfer rate to adjust to network conditions. Transmission Control Protocol incorporates several mechanisms to ensure reliable data delivery. The first one is acknowledgements. The receiver sends an ACK for received segments, confirming successful receipt of data. Cumulative ACKs acknowledge all bytes up to the ACK number, allowing the sender to know which data has been successfully received. Unacknowledged segments are retransmitted after a timeout period, ensuring that no data is lost. Next is timeouts and retransmission. The retransmission timeout, or RTO, tracks the round-trip time of segments. It is dynamically adjusted based on network conditions. Fast retransmit allows for resending segments after 3 duplicate ACKs, speeding up recovery from lost packets. Finally, checksums are used to detect corrupted data during transmission. TCP uses a 16-bit checksum, which is a ones complement sum of the entire segment. This checksum covers the TCP header, the data, and a pseudo-header. If the checksum is incorrect, the corrupted segments are discarded by the receiver. Transmission Control Protocol employs several techniques to manage network congestion and ensure efficient data delivery. The first technique is slow start. TCP begins with a small congestion window, typically 1 to 10 maximum segment size, or MSS. The window doubles every round-trip time, or RTT, resulting in exponential growth until reaching the slow start threshold, or STHRESH, or packet loss occurs. Next is congestion avoidance. After reaching the slow start threshold, the window increases linearly, by approximately 1 MSS per RTT. This is a more conservative approach to prevent congestion. The third technique is fast recovery. After detecting packet loss via duplicate ACKs, the congestion window is cut in half, and a new slow start threshold is set to this value. The connection then returns to the congestion avoidance phase. Let's compare Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP. TCP is a connection-oriented protocol, while UDP is a connectionless protocol. TCP guarantees delivery with acknowledgements and delivers packets in order, while UDP does not provide any delivery guarantees or packet ordering. TCP includes flow control and congestion control mechanisms, while UDP does not. TCP offers error detection and recovery, while UDP only provides basic error detection. TCP has higher overhead and latency compared to UDP, which has lower overhead and latency. Common use cases for TCP include web browsing, email, file transfers, and remote access. Common use cases for UDP include video streaming, voice over IP and video conferencing, online gaming, and domain name system queries. Let's summarize the key concepts of the Transmission Control Protocol. First is connection management. TCP uses a 3-way handshake to establish a connection and a 4-way handshake to terminate a connection. This ensures a reliable setup and teardown process. Next is flow control. The window size controls the data flow, preventing the receiver from being overwhelmed. It dynamically adjusts during the connection to optimize the transfer rate. Then there are reliability features. Acknowledgements confirm data delivery, retransmission ensures lost packets are resent, and checksums detect corruption. Finally, congestion control includes slow start, congestion avoidance, and fast recovery mechanisms. These features prevent network congestion collapse. If you want to explore this topic further, here are some suggestions. You can refer to RFC 793, which specifies the Transmission Control Protocol. Also, you can refer to RFC 1122, which specifies the requirements for Internet hosts, RFC 2581, which describes TCP congestion control. Finally, you can refer to TCP or IP Illustrated, Volume 1 by Richard Stevens. Further topics include TCP performance optimization, TCP security considerations, and modern TCP extensions. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.